Hello, welcome to a video on applications of the trigonometric functions. In this video we're going to solve right triangles, which is one of the most common things we do with trig functions early on. And then we'll look at bearings, and then finally we will look at simple harmonic motion. Okay, so let's get started with the solving a right triangle. So solving a right triangle, what does it mean to solve a right triangle? It means that we're going to find all side lengths and all angle measures in that right triangle. So typically we start off with a little bit of information. Like notice here we know this is a 90-degree angle, we know this is a 34.5-degree angle, and we know this side length. So we still have angle B to find, we have sides A and C to find. So you take the things that you know about right triangles in general, and then you have to start adding in some trigonometry to be able to complete the triangle for all sides. So the easiest thing to do here is to find angle B, because we're using the property that all the angles in a triangle have to add up to 180. So we've got a 90-degree angle already. We've got a 34.5-degree angle as well. So that means that other angle has to be 55.5 degrees, right? You could have also just subtracted that from 90, since it's a 90-degree. These are right triangles. So if you know one angle, then you just subtract from 90. So we know angle B is 55.5 degrees. All right, and now that we know that, we can start moving on to these side lengths. Now, how am I going to come up with the side lengths? If we knew what A was, we could find C by the Pythagorean Theorem, or if we knew C, we could find A by the Pythagorean Theorem. But since we only know one, we have to set up a trig function, and that's where the stuff that we've been talking about comes in. So I know this angle 34.5 degrees, and I know this side that's adjacent to that angle. So this is adjacent to the 34.5 degrees. This is opposite, and this of course is opposite the 90-degree angle, so this is the hypotenuse. So I need to set up a trig function that'll let me solve for A and C. So I could use the opposite over the adjacent with the angle, or I could use the hypotenuse over the adjacent with the angle. Either way, but it was like I mentioned in the last video, whatever I set up, I'd like to set up the variable in the numerator of the fraction. So I'm going to set up the tangent, right? Tangent is opposite over adjacent. The tangent of 34.5 degrees is equal to opposite over adjacent, so A over 10.5. Alright, and again that's opposite over adjacent. So that means that A, I just multiply both sides by 10.5, A is 10.5 times the tangent of 34.5 degrees. That's what it is exactly. Alright, but usually they'll have you round these things to a couple decimal places. So if I put in 10.5 times the tangent of 34.5 degrees, and let me go in here and make sure that I'm in degree mode. Nope, I wasn't. That wouldn't have been good. So I get 7.22 roughly. So I'm going to say A is about 7.22. Now you have to look and make sure that makes sense. B is opposite of 55-degree angle, 55.5. A is opposite of 34.5-degree angle. There's always going to be that relationship that the bigger angle is always going to be opposite a bigger side. So 55.5 and 10.5, 34.5 degrees and 7.22. So we do end up with a smaller side opposite the smaller angle. So that's good. If you ever got something like 12 here or something bigger than 10.5, then something went wrong with your setup. Okay, so just be on the lookout for that kind of thing. That'll always happen with triangles, is larger angles open up to larger sides, or on the opposite sides, that is. Now, all we have left is C. We could set up a trig function for C, but it's at this point we have the Pythagorean Theorem that we can use. So C equals the square root of these two added together squared. So 10.5 squared plus 7.22 squared. So once we get two of the three sides, we can find the third one with the Pythagorean theorem, because this is a right triangle. Now later on, we're going to deal with any types of angles. Any types of triangles. There won't have to be a 90-degree angle in there. And then we have to set up another trig function. Well, we'll have a way to do it. Alright, so there is our Pythagorean theorem, so we get 12.74 roughly. Alright, that was the C is the hypotenuse, so it needs to be the biggest of the three sides, and it was. So again, once you've found two of the three sides, you can use Pythagorean theorem, and once you know two of the three angles, you can just use the 180 rule that they have to combine to 180. Alright, so that's a very basic triangle, solving a right triangle. Just set up a trig function in there to find a second side, use Pythagorean theorem to find the third. Alright, for this one, we're in this hot air balloon. This is where we are initially, and our friend is recording us. So a minute goes by, and we go up this amount while he's recording us. So we started out at 31.7 degrees, and then we ended up at 76.2 degrees, and we want to know what was this value right here. What was this height? How much height did we go up in that minute that he was recording us? Okay, so what we're going to do is set up, this is 100 feet in both cases, so we're going to set up a trig function to solve for this a and this b, and then we'll just do b minus a, and that'll be the distance that we traveled that we're looking for here. Alright, so how do I find a? Well, this is 100, this is 31.7 degrees. A is opposite, this is adjacent. So once again, we'll use the tangent. Tangent is very useful for these types of vertical displacement type problems, because usually we can measure the ground. We can, because we're down there with the ground. This is what's typically hard to measure because we're not floating up in the balloon. So if we can determine the angle of displacement, and we have tools that can do that, we can easily measure things on the ground, and then the tangent function is then the most useful of the ones to estimate this vertical displacement. So the tangent of 31.7 degrees, this initial right triangle, tangent is opposite over adjacent, so tangent is a that we're looking for over 100. So a is going to be, multiply both sides by 100, 100 times the tangent of 31.7 degrees. So we're doing something very similar to what we just did in the last problem. So 100 times the tangent of 31.7 is 61.76 roughly. So that's how many feet high we are at that point, right? And then we're going to do it for B. So when we've elevated much higher than that. So notice the only thing that's going to change is this is going to go from 31.7 to 76.2. So we can just jump straight into this. B is 100 times the tangent of 76.2 degrees, which is approximately, I'm going to hit second enter, bring back the last thing I did, and change this to a 76.2. So 407.13. And then we want B minus A. We want the 407.13 minus the 61.76. And that'll be our displacement. So 345.37. feet. That's how much I traveled in that 1 minute straight up vertically like that. Alright, bearings. The next thing we're going to talk about instead of solving triangles. When we're talking bearings, we're talking about how I get from point O to point P but instead of just saying, the point coordinates like, 50, 75, we're going to say the degrees off of north or south. Okay, and we use an acute angle. Okay, we're always going to use an acute angle, so we're not going to say that it's so many degrees, like a obtuse amount of degrees east of south or something. We're going to say the closest acute angle. So if the direction we're pointing in puts us up here in quadrant 1, then we're going to base it off north, right? And if we're down here in quadrant 4, we're going to, instead of basing it off north and using a obtuse angle, we're going to base it off south. Okay, so we just always go to the closest north or south depending on which quadrant we're in. So 1, 2 will go to north, 3 and 4 will go to south, and we don't say it off of east or west. We do mention east or west. We're saying the degrees, so we're saying north is the closest from north or south. We're above the east-west line, so we're moving somewhat north, but then we say 65 degrees off of north in the west direction. So the way we would say it is north 65 degrees west. All right, north 40 degrees east. All right, and then this is south 70 degrees east. Okay, so whichever way we are above or below will be the first thing we say, and then the degrees off of that is the second thing we say, and then are we moving towards the east to get away from the south line, or are we moving towards the west to get away from that north-south line? All right, that's the last thing we say. So that's how we mention the bearing. It's always an acute angle. That's the important thing. All right, so let's name these bearings that we see right here, starting from A. So A. So here is A. Now this is a 20-degree angle off the east line, but that's not how we do it. Remember, we always say it off the north line. So if this is 20, then that means this angle is 90 minus 20, or 70. So for A, this is above the east-west line, so we're going to say north first. All right, and then we're off of that north line 70 degrees to the east. All right, so that's north 70 degrees east. All right, B. B, we are 40 degrees off of north, so we're not having to adjust from being off the west line. So B is ready to go. B is north. Again, we're starting off above. So B is north. This time it's 40 degrees to the west. All right, we move off of north in the west direction. All right, C. C is down here. That's off of the west. That 75 degrees is off of the west line. So we're going to use this because we need to be off of north or south. So 75 degrees from 90 is 15 degrees. So C is south. We're pointed south. And then we're to the left of south, so that's to the west. So south 15 degrees west. All right, and then D. D is, again, that angle is off of the south, so D is ready to go. It is south 25 degrees east. All right, we're 25 degrees east to south, 15 degrees west to south, 40 degrees north, west of north, 70 degrees east to north. Okay, but always put the north or south first, and then the degrees off of north or south in the direction of east or west last. Alright, so let's look at an application that deals with right triangles here. So this boat is leaving the entrance to the harbor. So here's our harbor. And it's traveling 25 miles, right, on this bearing of north 42 degrees east. Alright, so there's our picture. The captain then turns the boat 90 degrees from there and travels 18 miles on a bearing 48 degrees east to south, or south 48 degrees east. All right, and it goes that way. So question A says, how far is the boat to the nearest tenth of a mile from the harbor entrance? All right, how far is it from where we started? And then B is what's the bearing to the nearest 10th of a degree of the boat from the harbor entrance. So this right here would be what we're going to need for that. So let's see what we come up with. So the first part's easy. The first part is just the Pythagorean Theorem. So we went 25 miles, we turned 90 degrees, went 18 miles. So the value of C is just the square root. This is part A, by the way. The value of C is just the square root of 25 squared plus 18 squared. Alright, so to the nearest 10th it says, so 30.8 miles. Alright, and then the part B says, now we know that this is 30.8 down here. So we need to come up with this angle. Well, we know that this is 30.8. Alright, we know this is 18, we know this is 25. We can come up with this angle right here using the elements of this right triangle. Right? We can use any of these pieces that we want. This is 25. This is 30.8. This is 18. But this is the angle. So in this triangle, this is opposite the angle. This is adjacent to the angle. This is the hypotenuse. So it really doesn't matter because we know all three sides now which one we pick. So just to use the ones that they gave us, this was when we rounded. So these are exact. I'm going to use those two exact ones. So once again, I'm using opposite and adjacent just because those were exact values. So for part B, first thing I'm going to do is set up that the tangent of the angle that I'm after is equal to opposite, which is 18, over adjacent, which is 25. Right, that's the tangent of the angle. Well, how do I find that angle? Well, that goes back to one of the previous sections. If I know what the tangent is, to find the actual angle, I need arctangent. So the angle is the arctangent. Remember, that's what arctangent, arc-trig functions are. They're angles. So the angle is the arctangent of this output. Alright, so this is a positive output, which makes sense because it's a positive angle. And I just type that in my calculator again. Make sure you're in degree mode. You should be from earlier problems in this section, but just make sure you're in degree mode before you do this. Okay, we're in degree mode. So I'm going to say the arctangent of 18 over 25. And I get 35.75 roughly. So theta is about 35.75 degrees. All right. Now we need that because that's what this angle is. And for the bearing, we need to know how far we are off of that north angle. So if we add those two together, 35.75 plus the original 42 that's off the north, now we get how many degrees we are off of north, or east of north, if you will. So we're going to be north 77.8 roughly degrees east. So north 77.8 degrees east. Right, nearest 10th of a degree, so we rounded the nearest 10th. So north 77.8 because of the 5 there. Alright, so we had to get this angle, so we had to come up with that angle via I used these two sides. You could have used this, but because we rounded that, it's not exactly 30.8. It's best to use the ones that we had the most information on, and those were exact values. Alright, simple harmonic motion, that is a physical phenomenon in which we have this repetitive back and forth movement through an equilibrium, and the displacement on each side basically stays the same as time goes on. Now, of course, in these examples that we'll be dealing with, no energy will initially be lost. Just to kind of get the idea down, you can move along with it and kind of read a little bit in your book. And we do mention that, and obviously in the real world, real physical application and modeling situations, that energy would be lost over time, and so this displacement would kind of go away, meaning we would, instead of always going back and forth from the highest point to the lowest point, we would lose some of that energy over time, and we would make our way like something like this. It would just not get back down to those highs and low points anymore. It would kind of go away. We would lose that energy over time. But for these first examples, we are conserving the energy throughout, and we're having it just always has that same displacement all the way through while we're modeling it. Okay, the models become more complicated as we are allowed to start bringing in things like the stiffness of the spring, like have a coefficient for that, and have a number to represent the a way to represent the energy lost over time, friction, things like that, air resistance. All right, so let's look. Simple harmonic motion. So we're moving on. Initially, we're just going to describe something moving through a coordinate axis system, and because of that way that simple harmonic motion looks, the sinusoids model it really well. So the sines and the cosines. All right, A is our amplitude. That's how far we're displacing it from the equilibrium point. And the period is just how long it takes it to go through one cycle, just like it was before. All right, now notice that we're using omega in the place where we had b before, the number that's being multiplied by the input. So t is our input here. It's kind of like the old x was when we did these before, but t represents time. So when the independent variable is time, we typically use t. But omega represents the old idea of what b was when we were modeling this before. So we always divided 2 pi by b to get the period. Well, now we're just dividing it by omega to get the period. All right, and this is an important thing, that it's easiest to model this stuff if we're initially taking that spring and pushing it up like this, and this is t equals 0. If we're pushing it up and then we're letting go when time equals 0, then we would model it with cosine. Okay, but if it's at rest position initially and something strikes it, something hits the thing to get it to start its oscillation, then it's at rest position when t equals 0. That would be, not here, sorry. That would be like right here. If it was at rest position when t equals 0 and we hit it with something and it started its movement, then we would use sine. All right, if it was down here, if it was pulled as far as it can instead of compressed right here, instead of it being at its maximum positive displacement, it would be down here at negative. We would use cosine, but we would use a negative coefficient because we're pulling it downward. It's down below where it would typically would be. So depending on the scenario, the situation we're looking at, sometimes we use cosine, sometimes we use sine. Okay, but it's always, if we're starting in our rest position, if we're starting on the midline, we'll use sine. But if we're compressing the spring or pulling the spring down off of equilibrium, it's not just sitting there, in that case we would use some version of the cosine. All right, so a definite contrast between where the two would start. You can actually see when you're going to use cosine versus sine just by the scenario given. All right, let me move this to its own slide. So a ball on a spring is pulled 4 inches below its rest position. So we are starting below, there's the rest position. So we're pulling it down here and we're starting at 4 inches below. So we're going to say that that is negative 4 inches. Let me try to even that out. So this is down here at negative 4, and so that means the maximum displacement is going to be up here at positive 4. So this is a point on the graph. That's 0, negative 4, because we're at 4 inches below and we're releasing it then. All right, the period is 6 seconds, so I'm going to put a 6 right here and then a 12. And remember, the period means how long it takes us to get back to where we were. So there's that, there's that. And remember, we're using cosine here because we're starting off of the midline. We're pulling down to either a maximum or a minimum. Alright, and then remember, halfway between these two, halfway between 0 and 6, we'd find 3 seconds. Alright, we're up here at the maximum. Remember, for cosine, at the 1/2 point, we're at the opposite end. Alright, and then quarter points halfway between 0 and 3 is 1.5. At 1.5 we are on the axis, and then halfway between 3 and 6 would be 4.5. We're back on the axis. Alright, and so notice it's always 1.5, 1.5, 1.5, 1.5. So 1.5 and 1.5 would be 7.5. Alright, halfway between 6 and 12 is 9. And then 10.5. Same thing's going to happen. At 9 we'll be up here again. This is the second period of it. And then 7.5, we're on the midline. Alright, or equilibrium. And this thing's going to look like something like that. Alright, now D is what we typically use again for the displacement. D equals A cosine. So the A is the amplitude. The amplitude is from the midline to the distance, just like it was before. So amplitude is 4. But because we start off negative, we're going to use -4. Alright, and then this is cosine because we're starting off either at a maximum or a minimum. We're not starting off at the origin or the midline. So we're starting off with cosine. And then the period is 6 seconds. Remember, the period is determined by taking 2 pi and dividing by omega. So our period is 6. So switch omega with the 6. And I get this, and then just reduce. 2 over 6 will reduce to 1 over 3. So I end up with pi over 3 is omega. Alright, so -4 cosine, we multiply omega times t inside the cosine. So -4 cosine pi over 3 times t. That's our model for this thing. Alright, now let's look at it real quick. Alright, so I've got -4 cosine pi over 3 times x. I'm going to change my window. I'm going to start at 0. Doesn't make sense to start before that because we haven't released the spring before that. My maximum x I did 2 periods, so I went all the way to 12. Alright, and then my scale was 1.5. Alright, and then my y minimum was -4. I'm going to go to -5 to +5 just to have a little gap on the bottom so we can see the points. Alright, and then graph this thing. Oops, that means that I am in degree mode. I didn't switch back to degree mode. So let me go back. Y equals mode, radian. Alright, now graph. Alright, so there's the oscillations that I was hoping to see. And I'm right back to where I started a second time. So that's 2 pi. And I can just press trace and just like we've been doing before, verify these points. So 1.5 I should be on the midline, or at 0. Equilibrium. At 3 I should be up at the max at 4. Alright, at 6 I should be back down at -4. 9 back up at +4. 7.5, just checking the different points so we can see that it works. Alright, now let's think a little bit about this. Let's use our brains. Again, typically this wouldn't happen. If you pull a spring down, it's going to bounce back and forth. It's going to lose some of that energy. Now you can have springs that can conserve it for a pretty good while, but this is just not realistic that it would never lose its energy. But other thing that's not realistic is the time here. I mean, look how long it's taking to go one full cycle. Right? Think about 6 seconds. Pull a spring back and I let go of it and it goes up and down. And by the time it gets back down, 6 seconds has to pass. So think about this. I pull it back, let go. It goes up and then starts back down. And that just now it stops. That doesn't make any sense that it would take that long for a spring to do that. And again, the reason is just because we're simplifying it to have whole numbers. We're simplifying it to not lose its energy. We're just simplifying in the beginning to be easier just to kind of play with and work with it. Okay, so maybe if it was the period was 6/10 of a second or something, it would be more realistic. But we're just using whole numbers right now just to give you the idea and make sure you can model something that fits the properties, easy to check it to make sure it works. All right, so lots of whole numbers, lots of values of pi that we've seen before, pi over 3, just to make the first model you work with easy. All right, now you will see some more, that come a little bit more difficult later on, but just to start off, we use as many whole numbers and easy things as we can. All right, frequency of an object in harmonic motion. Frequency, notice this is omega over 2 pi, and the period was 2 pi over omega, so that just means that we got the reciprocal of the period for the frequency. So let's just use an example of how we use frequency with this. So a piano tuner, middle C has a frequency of 264 vibrations per second. I think it's a little bit less than that actually, but write an equation of the form D equals sine omega, all right, for simple harmonic motion. Well, 264 is our vibrations per second, so that would be right here 264 is replaced with that F, so that means that we're going to solve for omega and put it in to this form. We have to multiply both sides by 2 pi. So 264 times 2 is 528 pi equals omega. So that's what we would put in for omega in this thing. So D equals the sine of 528 pi